Okay, so welcome to session 2 of the Simulation Summer School, which is presented it's been organised in collaboration with the British Psychological Society's Maths, Statistics and Computing section and the Psychology Postgraduate Affairs Group, aka SciPAG. My name's Oliver Clark. I'm from Manchester Metropolitan University. I'm a lecturer there, and I sort of mainly focus on psychometrics and things like that. This presentation is heavily borrowed, i.e., almost copied verbatim from a session I did with Emma Henderson from Kingston University a couple of years ago at the SciPAG conference. All the materials available on OSF, Open Science Framework. It's got a load of worksheets and things like that, but most of what we're going to be doing won't need data sets. It's all going to be done in base R, so there's no, you only need to have R or RStudio or whatever your IDE of choice is installed. So there shouldn't be too many problems with that. The worksheets are really for you to take away and sort of practice on. If you bump into any problems with that, I'm obviously available by email or Twitter. So just give me a nudge if there's anything you want following up on. So first of all, I guess this presentation is going to go on for a little while. So while we're at it, maybe just make sure that you've got R and RStudio installed, because you're going to be needing that fairly soon. If you have any trouble with R or RStudio, you can also use RStudio Cloud, which works just the same. As I say, we're not installing any packages or anything, so base R will just be fine. You can just, I think it's cloud.rstudio.com, and you'll get like a sort of a environment there if you're really struggling to install it. So, in true lecture fashion, we've got some learning outcomes and objectives. So the outline is that we're really focusing on the idea of power analysis and using simulation to do this. So we're going to be introducing power in general and just talking a bit about what it means, how we establish it, the benefits of doing power analyses. And then we're going to be looking specifically at the simulation approach to doing power analysis. Now, Lisa DeVrine went into quite a lot of the package flow was absolutely amazing, I thought, and used the tidyverse implementation of R, and there was loads of complex designs. We're really taking a big step back. This is really just like a really beginner's introduction to power analysis using simulation in R. So I'm not assuming necessarily any specialist knowledge in programming or in like high-level statistics or anything. We're only going to be looking at t-tests, which most people would have covered in undergraduate psychology or like social science courses. In other words, just comparing two means to see if they're reasonably different or not. But the learning objectives for this session are that we're going to be trying to understand why it's a good idea to simulate data rather than just using rules of thumb or maybe like G-power, and also getting some hands-on experience of simulating real-life data with a little bit of data visualization. We're not going into ggplot because, again, I wanted to sort of start really, really basic. We're just going to be using sort of base R plots, which aren't as attractive. Brilliant. Okay, cool. All right. So as I said, I will delete that awkward silence from the analysis, and we'll just get straight into it. So I've just done the learning objectives, why it's a good idea to simulate data for your studies before you collect real data, and gaining hands-on experience. As I said, we're doing this from base R. We're going to be looking at functions to create random noise and to simulate means and things like that before analyzing it using like a t-test. Before that, I'm just going to talk about what power is. So power is the probability, this comes from Cohen in 1992, probability of observing an effect of a particular size if it exists. So this means that in the long run replications of a study that has a particular configuration, so in particular number of participants, particular alpha level, so and particular sort of false positive rate, what the likelihood is over the long run that you will observe an effect. So it's not necessarily the effect that you will find it in a particular thing, but it's you would observe it 90% of the time if you were to continue replicating if you had 90% power. So more power means that we're less likely to make a type 2 error. And this means that we're kind of you're thinking about it as the chance that your study will work if your hypothesis is literally true. And the way that I always find these type 1, type 2 error titles really quite confusing. I prefer to call them false positives, false negatives. But if you're interested, a good way to think about error rates is in the story, The Boy Who Cried Wolf, the villagers in that story commit a type 1 error followed by a type 2 error in that order. So there's some wolves. So generally we have we create this sort of table here, which gives us our decision. We reject our null hypothesis. If the null hypothesis is true, then the villagers have run up the hill and there's no wolf there. If H0, as in the null hypothesis, is actually false, then this is like the correct decision. This is what we're hoping to find. We only want to find really effects that are true in the real world, and that gives us the correct decision. And then if we retain the null hypothesis, we end up with a true positive, a true negative, or a false positive, which is our type 2 error rate. So yeah, in summary, it's the probability that in the long run we would observe an effect if it's there. Power analysis is determined by sort of three parameters. We have an effect size, which is the magnitude of the difference between, in our example of the t-test, two groups. So we have two groups. What is the magnitude of the difference between them? That's essentially the effect size. In things like regression and ANOVA and things, it takes on a different form, but it's usually the sort of magnitude of the effect that we're interested in. Also, the sample size, so how many people we actually have access to when we're collecting data, and the target power that we're willing to settle for. And this becomes like a bit of a balancing act. You hear lots of different suggestions about the target power. Some people say 80%, some people 90%, some journals like require 95%. But I think generally for undergraduate degrees, people are usually happy around 80%, which means that if you were to run 100 studies, you would miss an effect if it was there 20 times. And using any of these three parameters by changing them or holding one of them constant, we get three different types of like related equation that tells us something about our study parameters or our study configuration. These include if we know our sample size and we know the target power, then we can actually estimate the smallest effect size that we could detect using this configuration. So I suggest this to my students, station students. Sometimes I say, ideally, you want to have an effect size of interest in mind and then work backwards and figure out the sample size using that. But really, as an undergraduate student, you're unlikely to get more than 100, 200 participants. So maybe what I ask them to do is to do a sensitivity analysis, which is where they identify the smallest effect that they could observe in the long run with their sample size and their target power. So this is what we call a sensitivity analysis. There are options to do this in G-Power, and we can also do it sort of using simulations as well. If we have a target power and an effect size, this is like the ideal situation for this gives us an a priori power analysis. And this means that we can determine, given an effect size, which we may have estimated from previous research, similar studies, things like that, and we have a target power, so the amount of times we're willing to be wrong when we should be right about the actual effect size, the actual effect at population level, then we can estimate the smallest sample we would need to reliably observe that effect. And this is a priori power analysis. It's kind of like almost the gold standard, I suppose, for power analyses. And that's the sort of, and that's if we had unlimited resources and finding participants really wasn't a problem in the slightest, then this is the sort of thing we'd do. And then needs some brief mention. sample sizes and effect size, if we've already collected a sample and we know the effect size, you can estimate the so-called power of the test, which is called as post hoc power analysis. But we don't really do those because they're just transformed p-values. It doesn't give you any additional information other than the p-value. Although Lisa DeBryan on Friday did give an example of when post hoc power could be useful. It was in a simulation study that replicated a series of 6 studies repeatedly. They used observed power in that, but that's really the only sort of feasible use case for that. So we're really kind of just interested in sample size and in a priori and sensitivity analyses. And as you change these different parameters, you end up with these things called power curves. And I'm just focusing on Cohen's d at the moment, so standardized mean difference between 2 variables. And as we see that with smaller effect sizes, so smaller Cohen's d, we need far more participants than we would for a larger effect size. So anything above 0.8, and we're hitting sort of over 80% power with sample sizes of 80. Whether a Cohen's d of 0.8 is a reasonable effect size to expect in your research is down to like your own individual fields. It can happen, but in psychology we usually have quite small effect sizes. So one of the worksheets that we're going to be looking at, not necessarily today, but one of the things that you can go off and do in your own time, actually shows you how to create one of these plots. So you put in a series of effect sizes and a series of sample sizes, and look about how the amount of power changes as a function of the number of participants that you have, or maybe not participants, samples as well. It could be that you're dealing with I don't know. I just wanted to say stool samples for some reason. Why did that come to my mind first? And so those number of samples. And you can almost track the amount of power that you can achieve from different effect sizes and sample sizes. Just got a couple of messages. Oh, okay, right. So you might be wondering, why should I bother doing a power analysis? Well, this gives you more informational more information. There's a lot of informational value to doing a power analysis before you do your study, because then you can say how confident you are that in this effect that you've observed, given all the parameters that you've specified. If you have higher power, and again, power is relative. It's not. There's no high power. It depends on your effect size. So saying something's overpowered depends on size of your effect size and different areas of your fields and things like that. But you have a higher probability of finding an effect if it's there with a higher power study. If you've got lower power, you don't really learn much. There's a paper by Kate Button and others called Power Failure, which is an excellent paper, which goes into why having low-powered studies for the effect size that you're looking for is dangerous, because you end up not knowing what the effect is, and if generally if we use a p of less than 0.95 as a decision rule in order to publish and things like that, we end up with these really inflated effect sizes which are unlikely to be replicated with those. It's almost like a fluke. We can end up with a large effect size which we can't replicate. And so we're not sure whether there's a true effect. People will observe that effect size, treat it at face value, and then try and replicate using your configuration, and then there'll be a failure to replicate. And it's just it's got really low. It's called the Proteus phenomenon, and yeah, as I say, it's an interesting thing. It also means that we can limit our resources as well. So studies are really effortful, time-consuming, and expensive. There are ethical issues with using human participants and things like that, particularly and in animal research and things. There's plenty of ethical issues, and we need to be using the minimum number of participants that we can get away with, and we don't know that until we do a power analysis and have an understanding of our effect sizes. Power analyses are free. G-Power is free, R is free, the power package is free, simulation is free, as long as you've got a computer, access to the internet and electricity, so they can be relatively quick as well. and it gives you information as to whether a study will be worth your time. So is it actually worth, if you've got if there's an effect that you're interested in and the effect size is so small that you'd need 10,000 participants to reliably find it, is it really worth your time? Is it an important enough question at that point? In some cases, I'm sure it would be. But in some cases, if like the priming effect or something, is it really that, if something is that small, is it really going to be affecting us in day-to-day life? Anyway. Also helps us increase chances of replication effects, use of prior effects. If we can power our studies appropriately, and also increases the precision of estimates. So there's loads of different reasons why we would have to do power analysis, and I'm sure I am preaching to the congregate, whatever here. Okay, so a power analysis is also factual rather than a rule of thumb. I often see cited in dissertations this Green citation. So Green from, I think it was 98 or something, said 20 per cell is appropriate or something. It's just kind of, it doesn't take into consideration your effect size of interest. It doesn't take into consideration, it assumes a p-value of 0.05 as a decision rule. And a power analysis gives you a factual thing that you can include in a paper or dissertation and refer back to in your discussion. And it also means you can justify your sample size to reviewer 2 if you need. Also, as I've also said, hang on, have I already gone through this? Yeah, I think that's repetition. Okay, don't repeat. So that's a long-winded and sort of quick, like a surface tour of power analysis. I'm going to talk a bit about the second part to this this workshop, which is simulation. And what is simulation? It's whenever we do social science with humans or anything, we always assume that there's this sort of idealized generating process, data generating process, particularly in deductive methods, a data generating process that's floating in abstract land that is creating data. And it's whenever we take a sample, we're actually tapping into this data generating process, and we are and as we observe these samples, we're trying to get an idea of what is going on in this weird abstract latent land from what we observe in the quote unquote real. So any hypothesis that we might have, we're assuming is representing a data generating process. So it's like a model that is representing something that is in reality. Now we make various assumptions about this data generating process, and because we are mere mortals, we generally think in straight lines because that's easier. You can go non-linear if you like, but for the most part we teach the general linear model. And we have to assume that under the general linear model, that data are randomly sampled. That covers us for like selection biases and things like that, and tries to give us as like unbiased an estimate of any parameter that we have. We also assume that the underlying effect is actually follows a straight line. So the general linear model, as I heard Dan Simpson say once, is like, pro tip, draw a line through it. That's my favorite definition of the linear model. And that any effect that we have will be masked by error. So what we're aiming to do in sampling statistics is estimate this process that's occurring using samples, and we try and fit that to a straight line. And if any of you have read Andy Field's books, you'll be very familiar with this equation, which is the one that we use to model behavior, attitudes, anything in social sciences. And it's just the equation for a straight line. So y, the y-axis, is equal to the intercept, so beta 0, plus a series of predictors, and then there's some error at the end. And what we do in simulation is try to recreate this this equation and almost represent our hypothesis, which is contained within this equation, using like random number generation. And you can do this in any number of ways using dice and stuff, but it's much quicker to just do it using computers. So what we're going to be doing is, oh, we've got some meta humor, avoid unnecessary repetition in science. That's the next slide. Thank you, Sarah. So here we're going to be looking at throughout this whole session, and we're going to get onto the coding very soon. We're going to be looking at comparing two means using a t-test. So what we're going to essentially be doing is imagining an effect, and we might be thinking of a headache drug. This drug has an unknown population effect. So if we gave the population of everyone who has a headache this drug, it would have some effect on their pain levels. We can never know this because we can never track down every person who has a headache at any one time. It's also a transient state, so it's very unlikely that this ever happen. So we just take samples of people with headaches, give them this headache drug, and see what the effect is, and try and estimate this this mean effect of pain reduction based on this drug. And as I say, we do estimate this effect using samples. So we might take 100 samples of people with and without headaches, give half of them a placebo, give the other half a aspirin or something, and then our hypothesis is that our second group, the mean 2, is going to be less than mean 1. So people who've taken the placebo are going to have greater headaches than people in the second group. The outcome of mean 2 then is therefore equal to the placebo group plus the effect plus random error that's acquired through sampling errors and things like that, which we assume will even out eventually if we have like a 10 million participants. So this description of a very simple study design easily fits into the linear equation here. We've got our outcome is equal to this placebo group plus our effect plus error, and just keep this in mind because this thing is the same for every kind of level of statistics in the linear model. It's the same equation for regression. It's the same equation for ANOVA. All these sorts of things. We've always got a baseline, we've got an effect, and we've got error as well. And what we're going to be doing using R very shortly is we're going to be using this equation to simulate an effect thousands and thousands of times to see how the p-values vary the average p-value varies as a function of like sample size and effect size. And we'll do this by randomly generating data for a hypothetical study that conforms to a predefined model. I've just so I'm doing some meta humor again. So repeating this thousands of times to simulate thousands of replications of this study. We then analyze these results to see if the effect is significant, and then we aggregate all these results, and eventually what we end up with is an estimate of the power of this configuration of studies. So for a given effect size and a given sample size, what is our estimated power? And we do this just by looking to see how many p-values are less than 0.05 once we've repeated a study thousands and thousands of times. Caveat here is that we're dealing with idealized distributions. We won't see any skew here. We won't see any kurtosis. We won't see any of the other horrible nightmare things. We won't see any missing data. Although if you were here on Friday and you saw Lisa's talk, her faux package has some interesting ways of creating skewed and like unidealized data. So the designs we're going to be doing here could be done in GPower very simply. It's just a matter of entering the data and getting a number out. Most of them are going to be fairly trivial to do mathematically. But as the more complex you go, the more that simulation helps. And another nice thing about simulation is that with GPower, you just put some numbers in, you get numbers out, and then you're like, okay, my study is powered sufficiently. As Stanley Lazek said when I did a workshop with him a few years ago, he was delivering this workshop. It's like, if you know how to simulate your data, you also know how to analyze it, because the same data generating process used to create the data is used to analyze it. So that's another benefit of doing simulation, is that by virtue of simulating the data, you already know how to analyze it. So it's like a reversible process. And so the process also helps you plan. So we know you've already thought about your minimum effect size of interest. You've thought about your sample size, your power, you've justified your alpha, all these sorts of things. And it also means that you can specify your confirmatory analysis plan. Because as you're going to see when we finally get to the R code, you're creating the data, then you're analyzing it. So you've created it, you've analyzed it, you've done both things. You can send that off to a reviewer and say, look, this is exactly how I'm going to analyze my data once I've got it. This is what it's going to look like. So it's really useful for things like registered reports. It's useful for pre-registration, and I can't recommend it enough. So the list of utensils that we're going to be using today, we're going to be using R and RStudio. That's our kitchen, that's our environment. We've also got a set of utensils. We're going to be using the ARM or rnorm function, which you may have come across. Lisa mentioned it briefly in on Friday. We're going to be doing a few loops as well, which is so like a for loop. It's in every programming language. Hopefully you've done them before. If you haven't, oh, I think someone has just unmuted themselves. Yeah, if you'd like to mute yourself. Okay, cool. We're going to be using loops. So the idea is that we create random numbers and then do that 10,000 times without having to click the button over and over again. We then going to be using the function called which tells us which cases meet a particular condition. In our case, it's going to be which of these cases meets the condition of p is less than 0.05. And we're also going to be using t.test, which is Welch's t-test. It's slightly different from students' test in that it has a correction for different variances, which is kind of more the norm than in social sciences than it probably was when student was brewing Guinness or whatever it was in the 19th century, 20th century. So we'll be using Welch's t-tests. And then we've got a recipe, which is our general linear model, which is y equals intercept plus effect plus error. So we're going to be moving straight on to some live coding now. A quick question. Pauline, someone's just asked a question as to whether simulation doesn't work for exploratory research. so I'd say you can use it to explore the area in which you're in. So, but it could be useful for, like, if you've got an idea for an effect and you're trying to observe something in your field, what's the outcome of the statistical tests that you're going to be using is given the data that you've got. So you can do exploratory simulation studies, absolutely. But ideally, if you're doing a hypothesis test, you really want to be knowing how you're going to analyze it beforehand, because always you end up introducing research degrees of freedom into your design. Maybe you could tell us a bit more. What sort of question are you going to be asking? Or maybe now's not the time. You can email afterwards if you like. So I'm going to move over to R now.
Got another question, Ollie.
What's the question?
The question is, what do you mean by the smallest effect of interest, and why should we use it in our power analysis?
That is an excellent question. Thank you very much, David. Okay, so smallest effect size of interest is, there was a study a few years ago on Facebook, and they, without getting consent from participants or from users of Facebook, they started trying to manipulate people's emotions used by presenting them with different different content that had was valence differently, so it might be negative or more positive, and they analyzed people's like the content they were then posting, and found that people were more negative after they read after they've been presented with sort of negatively valenced content. So it's kind of unethical because there wasn't any it was kind of A/B testing and there wasn't any consent involved. And this sort of was a highly significant effect. It was like the p value was like less than 0.001 or something. However, they had like 14,000 participants in that study, and this effect size was equivalent to 1 word per 1,000 being more negative in that group compared to the group of people in the positive group. And that effect size was so small that it was unlikely to have been affecting people at a sort of conscious level. It was kind of almost, it could almost be called an artifact or something that is so small to be clinically relevant or useful. And that's what we mean by smallest effect size of interest. If Facebook had said, okay, so we're really interested, if people are like, I don't know, writing a paragraph or a sentence that is more negative than in the negative condition compared to the positive condition, that could be seen as, or it's like they've had like a coherent thought that is more negative because they've seen this content. If they'd specified that before they did the study, you could say that that one sentence would be their smallest effect size of interest. Anything less than that, they're not particularly interested. Anything more than that is sort of relevant, interesting, etc. You could do this also for in social science as well. So it might be that we try and replicate the barge study where people walk slowly towards an elevator after being primed with being elderly. If they slowed down by like a meter per second or something, so they were considerably slower. If you could specify that a priori and say, okay, so I'm not interested in anything less than say half a meter per second slower, then anything below that you see as being a sort of an artifact or something that's not meaningful in reality. And when you specify a smallest effect size of interest, you're basically making a stronger claim about your effect. You're saying that I'm confident that this effect is going to be clinically relevant or sort of theoretically relevant, and anything smaller than this will essentially treat as zero. And this comes into equivalence testing, where and things like that. So the reason we should be using it in exactly, yeah, exactly. So I just said, can I define the smallest effect size as, let's say, 20 milliseconds difference in reaction time? Yes, that is an excellent example. So anything below that would be beyond human perception. Yep. Anything above that, we're starting to get into sort of a level of interference that would be like actually of interest. We've got Sarah saying, if we care about, say, health research, if your medicine taken daily increases lifespan by 1 day, that isn't all that large of an effect. Your smallest effect size of interest for medicine might be the difference, a difference in days, weeks, or even years. You have to say, even if the effect is significant, at what point is the effect so small that I don't even care that it's significant? That is a far more succinct way than I could have put it. Thank you, Sarah. So what we want to be doing really is we want to be powering our study on at least the sort of a minimum of the smallest effect size of interest. Anything below that, we're wasting resources. If we need 10,000 people to get an effect size of 10 milliseconds, when really we're only interested in anything above 20 milliseconds, we're wasting participants, wasting money, wasting time. And yes, brilliant. Thank you. And Farid Anvari and Daniel Lakens have a paper here, which is now in the chat, which is about determining the smallest effect size of interest. Joe Hilgard has also looked at like largest effect sizes of interest as well. So like at what point, if you literally tell a participant what to do, what is the size of that effect? And anything larger than that is likely to be sort of unnatural, if you like. So does that, there you go. Thanks everyone, thank you. how do you translate 20 milliseconds into an effect size, like a partial F squared? You'd need to know the context. You'd need to know the means. So what you'd do is you'd probably go into similar research that uses a similar method to you. You would look at the kind of means and standard deviations around that, and you'd see what a 20 millisecond difference means in terms of that, then convert it into Cohen's d if it's just between two groups. And from there, you can then translate into a partial F squared using, there's some equations somewhere. I can send you a reference. I haven't got it on top of my head at the moment, but if you send me an email, I can send you the reference for that. But yeah, so you'd want to see what kind of range of, you could use a meta-analysis, for instance, and see what 20 milliseconds sort of equates to in terms of like the means and standard deviations in those kind of studies. Any more questions before we get going? Okay, right, so we're going to full screen mode. So this should all be familiar to you if you've installed RStudio by now. We've got all the windows. Can everyone see the entire screen, or is there? Oh, hang on, I'm going to move zoom to the bottom. That's better. I'll move that to the bottom as well. Right. Okay. Cool. So as you can see, very sort of generic setup. It might look a bit different in yours. We've got all our files down here. We've got access to plots, packages. We've got our console here. I'm going to clear that because that's dirty. There we are. And just in case some people in here have not used R before, I know there's one person in here who is a TypeScript developer. Let's just quickly do our inaugural R user interaction. We'll just go print hello world, and that says hello world. Right. So now some of you will have written your first line of R code. We're all should be on the same page now. We're going to go to File, New File, and R script. That gives us a new file. I'm going to save this now as Power Workshop. Yeah, that'll do. Okay, so where to start? I guess what we need to do first is just create a random number, because that's what we're interested in. We're interested in simulating noise and means and effects from this fictitious latent generating process, and we're going to do this using a function called rnorm. So that's just typing rnorm. I might zoom in a bit. Rnorm, and rnorm takes three arguments. It takes the number of observations, a mean, and a standard deviation. So if we just type in rnorm by itself, we get nothing. If we put a 1 in, we get one normally distributed observation that has a mean of 0 and a standard deviation of 1. This is like a standard normal distribution. If we do 10, rnorm 10, we end up with 10 of them. And if we keep mashing it like that, we just end up with different numbers every time. So we could just do this over and over again, add them all up by hand, divide them by the number and get the mean, but that would be a complete pain. So what we're going to do is create a variable, and a variable is a container that we put these numbers in, and it will give us a so-called vector that contains 10 numbers normally distributed, and we're going to call this my variable. And in R, if you're a TypeScript developer, we assign values to variables using a arrow like that. This is kind of canonical R stuff. We go my variable it is made up of rnorm 10. We do that, and then in our global environment, we end up with my variable, which is a vector, 10 elements, and all 10 elements. When we actually look at it, my variable. There we are. Now with this vector, we can now run arithmetic on it. So we could go sum my variable, not mu variable, my variable, and that gives us, if we add them all up, we get 4.24. But we're not really interested in that in the sum. We're going to do the mean. So mean for this is just mean. Mean is 0.42. Problem here, because we know that this rnorm, I'm just going to put the numbers in as well. Mean equals 0 SD equals 1, we know that our population mean is 0. We know this is a fact because we've told it that. This R norm function, we've told your mean is 0, your standard deviation is 1. But when we take a mean of this, we're getting 0.424. That's an issue. That is that would be a problem because we've overstepped our known population mean by almost half a standard deviation. Huge error. And if we mash it over and over again, we're about half a standard deviation off almost every time. There, we're really far away. We're negative 0.69, 0.7 there. You're getting close here. I'm going to ask in the chat, how do you think we fix this? And I know see if anyone can come up with that. How do we fix this? We've got any answers? Increase n, brilliant. Yep. You can use that seed if you like, but it's more fun if we let's add a bit of chaos into our code. Well, you can use set seed. So what set seed does is if I was to go set.seed and put in like 24601, this sets our seed to our random seed. So that means that every time I run this now, we're going to get the same numbers out. See? Oh. Yeah, there we are. Set seed gives us the same number every time, which is boring. We want a bit of excitement in our life, so we'll keep we're gonna take set seed off, so we end up with different numbers every time. And people in the chat have given us exactly the right answer. If we want to make this mean more representative of this population mean, which we know exists, we just we need to increase the sample size. So I'm just going to pump it up to 100, and we end up we're much closer now. We're kind of a fifth of a standard deviation off there, but more or less we're getting smaller variables. And if we then like go overkill. And we go, let's do a million. This is my computer can handle it. We end up very, very close to 0. So this is just showing sampling distributions. The larger the sample size, the closer we get to our population mean, which in this case we know, and we make that assumption. We don't know the population mean when we're doing data collection in real life. It's not something we can ever possibly know, but using these little functions here, we can see how statistics respond to larger sample sizes in the ideal, and then kind of we just have to hedge our bets a bit in the real world. Anyway, so we've now created my variable. It's we've taken the mean. We can also do the standard deviation as well. So this works exactly the same with standard deviation. So standard deviation, my variable, we should expect it to be 1 at a million, but as with the mean, the smaller the sample size, the less the less accurate the standard deviation will be. So now we've got a mean and standard deviation of this, and yeah, great. We're now describing our sample sizes quite nicely. I'm just going to do a bit of environment hygiene here. We'll just delete that, remove the objects. So we're all starting from scratch. So what's next to do? We've got one mean, but we very rarely deal with one mean in any science. What does one mean tell us? We generally want two means. So let's see what happens. Let's see what happens when we create two means. So what we're going to do is create two variables. I'm just going to call them. I'm a lazy typist, so I'm going to do MV1 and MV2, and we're going to do exactly the same thing. R norm. And we'll start with 10 and we'll go from there. Mean equals 0, SD equals 1. This is going to create two sets of numbers. They'll be different, but they'll basically be the same. Basically here there'll be no population difference between these two variables, but we're just going to hardwire one in. So we're now going to turn this into 0.5. This tells us that the difference between MV1 and MV2 is a difference of half standard deviation. And so when we run that, we end up now in our global environment with two variables, my variable 1, my variable 2. Both of these are standard normal distributions. We would expect both of them will have standard deviations of 1. One will have a mean of 0 and one will have a mean of 0.05. But well, if you know, should, they won't necessarily, they almost certainly won't. Let's have a look. Mean MV2 is actually 0.02, so that's actually tiny, but again, we've got a small sample size. If we want to compare these two means, quite simply, all we do is type in t.test and then MV1 and MV2. Run that, and that gives us a Welch's t-test of the difference between these two variables. We've got a sample size, degrees of freedom of 70.53. This is the adjustment that Welch's t-test makes on this. It's obviously detected different standard deviations, which is because we've got rubbish sample sizes here. It's taken an estimate of minus 0.5 for mean 1, and mean of y is 0.02. So not only are we wrong here, we're actually the opposite in the opposite direction, and it's not significant anyway. But if this was significant, we'd be in completely opposite direction. We know for a fact that the mean of MV1 is 0 at a population level. We know for a fact that the mean of MV2 is 0.5 at a population level, and yet this data here has given us exactly the opposite direction. So let's fix this again. So maybe what I'd like you all to do now, we're going to all run a single, we'll go up to 15 participants. 15 participants, mean difference of 0.5, and we're going to run a t-test. And I want everyone to run this at the same time. I want anyone who gets a significant result to put their hands up, just like an emoji in the chat box. Let's do that. Have I got a significant? I have not. I don't get tenure. I fail. I end up working. You know, my research time has just been cut. Significant. Oh, we've got one person as a significant. What is T in this kind? Oh, we'll come back to that in a moment. Someone got a P of less than 0.01. Significant. Brilliant. Let's hear your Mahmood. Is that you've raised your hand because you got significant, or have you got something to say? If you've got something to say, please do talk. Is anyone on the cusp? Has anyone got a trend towards significance? Everyone who's just got a everyone who's just got a P of 0.01, you've all just got your JPSP paper, and you're on your way to greatness in a Russell Red Brick University. Garrett Bullock, have you got something to say, or is this just saying that you're significant? Well, I'm not happy with this. My career has just gone down the drain. I'm going to there we are. Now mine is below 0.01. I've just p-hacked my way to greatness using 30 participants at a time. What we've just done there on a large level is run a simulation. And because our norm is independent every time, that's essentially the same as running that simultaneously around the world as running simulations over and over again. Now, what we could do is find out how many of you got significant results and how many of you got non-significant results, and from that we could probably work out the power of this particular configuration when we have 15 participants, a mean of 0 for the first one, and an effect size, a standardized effect size of 0.5. But that's not very useful. We don't really have, I don't have that many friends. I'm not sure about everyone else. And fortunately, my computer is fast enough that it can do 10,000. I can make 10,000 friends immediately. And we're going to do that in a moment. A trend significant. Oh, right. So maybe you'd squeeze into a human factors journal. Probably not JPSP, though. Right. Okay, right. So we're going to go. What we need to do now is we're going to be. Oh, I'm sorry. We had a question from Auto Thoreau saying, what is T in this context? Now, T is a statistic that is a critical value that we compare against a table of things. And it basically tells us at a certain level, we can be confident that this difference between the two means would reoccur if we were to continue doing this study over and over again. So it's like a critical value. Anything above a particular T value gives us like a critical value where we can be a bit more confident that our effect will reject the null. So it's like a critical value that we're comparing our data to. Yeah. Sarah's on fire here. It's similar to a Z value. It's a standardized mean difference where you're correcting by the standard error of difference between the two means. Okay, right. So, has anyone here also? Are people in here familiar, or at least comfortable? I have heard of loops, for loops, because I can go into a little bit more detail about this if you like. But if I don't need to, then so people have, yeah, okay, right. So we're fairly okay with loops. There are, if loops are completely over your head, and you're too nervous to say anything, don't be nervous. You can DM me if you want. That's absolutely fine. But I can also direct you to resources where you can learn about them. So what we're going to do is set up something called a for loop. And these things have been around since, well, it's one of the main building blocks of computer programming. I was using them back in '96 on QBasic, if anyone's that old. So what we do is we're using a command called for. We type that in. Now, what for does is it takes a vector of items, numbers, things, and then does a set of commands every time for each element in that set of things. And the things we need for this are we need an index, so we need a value that contains the current iteration, if you like. So what we're going to do is we're going to say for this run. Let's go to camel case because I'm fed up of typing in like underscores for this run. So we're running this this mean study. I'm pointing at the screen, but you can't see where I'm pointing. We're going to be running this study 1,000. We'll just do it 1,000 times to begin with. For this run, in 1, 2, 1e4 or 10,000. Depends if you want to use scientific notation or not. What this is going to do is that this run here is going to take on every number between 1 and 10,000. In fact, some people might have slower computer. We're just going to go to 1,000. So for this one, in 1 to 10,000, this one is going to take the value from 1 to 1,000. And just to apprise yourselves of that, we're just going to say for print this one. And when we run that, just like it just counts from 1 to 1,000. So if you ever want to count to 1 to 1,000 and can't be bothered, just type that small line of code. But it doesn't have to print this one. You can also print, I don't know, hello world if you want. Why not? And then we'll get 1,000 hello worlds. So that's 1,000 of my friends have just done their first line of code. Right, okay, so from here we're going to create well, we don't even need to type. We're just going to copy and paste because we're lazy typists. We're going to go from Control C or Command C, Control V, and now what this is going to do is create 1,000 t-tests. What we don't want to do. I'm going to reduce this to 10, just because otherwise I'm going to end up with 1,000 things on my screen. And it's done it. If I then type in, well, never mind. So what that's done is just run 10 t-tests with these two random variables. But what we really want to see is the actual t value, p value, confidence intervals, things like that. And what we need to do with that is we need to actually store our t value, our t-test, into a variable because otherwise we can't access it. So we're going to go my t is equal. I'm going to be Mr. T is equal to t.test m1 mv2. Do that, and what we now have is every time I type in Mr. T, we're going to get I pity the fool. Oh, we don't pity the fool this time because we're less. No, we're above 0.05, so we are pitying the fool here. Okay, so we now have an object, a list, I think it's called, of everything that we need to know about this particular t-test, and we can access that using R's index feature. So we can now go Mr. T $, and we get the statistic. We can access the parameter, the p-value, confidence interval, estimate, yada yada yada. Because we're frequentists and maybe we're doing our research 10 years ago, we're only interested in the p-value, so we're just going to do that. So Mr. T $p-value, p.value, gives us the value of the p-value from that particular t-test. And so what we're going to do is actually print that to the console. So we're going to go Mr. T is equal to t.test, and then we're going to print Mr. T p-value. and then we're going to see how many times we get pitied. Right. Okay, so we've just run 10 independent t-tests on a sample of 30, mean difference of 0.5, and a standard deviation of 1. We've got how many significant findings? Well, I've got three significant findings. How many has everybody else got? 3. We go to the chat. 3, 2, great. So we've got yeah, kind of underwhelming. But rather than counting, let's get fancy, shall we? Actually, we'll carry on counting for now. So my p-value. Okay, so what we could do this, I don't know, 100 times, and then we end up with 100. I wouldn't suggest you do it, but you know, we've now got 100 p-values. I don't really want to scroll down and count all this. Fortunately, the computer can do that for us, and we're going to do that using something called a matrix. Now, a matrix is going to get fancy, two-dimensional vector. All right, so it's basically it has rows and columns. For our purposes, we're just going to use one column, and we're going to have for this case, we're going to have 100 rows to our column, and we're going to go my matrix. We're going to call this Keanu. Keanu is equal to matrix, and we're having n rows. This takes several arguments. We want to give it a number of rows and a number of columns. The default is 1 and 1. We want to give ourselves n row of 100 for now. Okay. We've now got Keanu is now a matrix. It's one matrix with one row. It's the one Keanu. We type that in, and we've now got 100 rows of NA. So NA gives us nothing. This is the stuff of nightmares. If you download your Qualtrics survey and you get this in where your data is meant to be, that's enough to keep you up at night. So we've now got 100. We're going to fill this in with data, though, which I do not suggest you do if you do download your Qualtrics file, because that would be data fraud. But so we've now got our matrix called Keanu, 100 rows. And what we're going to do is we're going to iterate. This is what we call it, a for loop iterates. We're going to go do 100 t-tests, and we're going to store our p-value in Keanu. So we're going to go from Mr. T. We've just created Mr. T. We're going to say Keanu, and we use R's index again. So R, to index a row on a matrix, data frame, anything, we use square brackets. Can't do them. I haven't got square hands. And we type in a number. Now, what we know is that this one is taking on the number of the loop that we're currently in. So if we type in Keanu square brackets this run, the first time it runs, it's going to look for Keanu row 1. Then second loop, it'll be Keanu row 2. So what this will do is now for every loop, it'll go down the matrix. Until the bottom, until we get to 100. Now, rather than printing our p-value, what we're going to do is assign a row in Keanu with Mr. T $p.value. Now, what this is going to do is it's going to store 100 p-values into a matrix. And then we run that, and we type in Keanu, and we've now got 100 p-values, okay? What is the power of this? How do we work out the power? Well, we work out the power by taking the mean. If we take the mean of all these, we're going to end up with the mean p-value across 100 replications of this study comparing to two variables. So we go mean Keanu. We just got to say, we don't want to be mean to Keanu. He's a nice guy, but we're going to take the mean there. 0.25. That's our average p-value. Okay, that's not the power, that is our average p-value. So it's a bit underwhelming. We've done all this. We've got a mean p-value of 0.25 odd. But how many of these were significant? How many of our applications were significant? I mentioned one of the ingredients, or one of our utensils for this recipe. I'm not going to strain the kitchen metaphor too far, but one of the utensils was the which function. So we've got which. And this basically, we give it a set of data. So we're going to say which Keanu is less than 0.05. So we want to know which of the rows in Keanu are equal to are less than or equal to 0.05. And we do that going which bracket And then we go Keanu is less than, we're not even, we're only interested in less than 0.05. Okay. And that tells us that there are 31 Keanus that are less than 0.05. We can see that just by looking at the number of entries in this vector. We might be feeling lazy. We don't want to look that hard at it. In which case, we can just go length, and we just take the length of that vector, which is exactly the same as looking at those numbers, and that gives us a power of 30. Well, it's not. Yeah, it gives us 31% power. So 31 of these replications gave us the we made the right decision that there was a difference between these two 31% of the time. It's fairly trivial to change the sample size, but what we're going to do is use another variable, because always we've got to go type over and over again. So what we're going to do is say n row equals, we'll call it k, okay? So, and we're going to say k equals 100. So we're going to go to 1,000 now. We'll go to 1,000. So Keanu is now going to be 1,000 rows long. And it also means that we need to change the number of loops that we're doing as well. So this one in 1 to k, that means that we only have to change one value instead of two. It's just like shorthand. We're being lazy. Now we do this, we end up with 1,000 replications. So we've just done a power analysis on this study with 1,000 observations, and we can once again do a length thing, and we're balancing around 30% power. So not particularly good. This norm of this sample size of 15 is not doing us any favors, really, is it? So maybe what we can do is try and increase the sample size. What should we increase it to? Who wants to chuck in first person to say the sample size? Yeah, we can also do that. That's right. That's good. Fabrice, you've blown my mind. You do have to. Oh yeah, thank you, and thank you, Sarah. Yes, we do have to define Keanu before the loop. Yes. Okay, so give us a sample size. 80 per group or in total? Per group. Wow. Okay. Someone's got loads of money. And prolific. Okay, so we're going to change that to 80. So that's all we have to do. We have to change our norm number of participants to 80. And then we just run it again. Here we go. Now we've got 90% power. That's what that's telling us. We're saying if we have 80 participants and a mean difference of 0.5, then we'll correctly find that effect size 90% of the time. And that's kind of the level that we're looking at when we're doing real research. And bear in mind that this is a t-test. This is like the simplest thing that you'll do, other than maybe a chi-square. It's one of the simplest tests that you'll do in psychology, and you still need 160 participants to reach 90% power for a mean effect size of half a standard deviation. If you think about the range of kind of effect size you observe in psychology, they don't get much bigger than that unless, like, I don't know, you're drilling holes in places where holes shouldn't be drilled. So we should be so just bear in mind that just because the t-test doesn't mean you can get away with a small sample size. Right, okay. Another thing we can do as well here is we can also do a histogram, and this is on worksheet 2 if you download the worksheet. Oh, sorry, worksheet 1.5, because I added it after 2019. So what we can do is R has a really nice function called a hist. We just do hist, Keanu. We do that, and we get a nice histogram giving us the distribution of p-values under this effect. And as we can see, we're pretty much positively skewed. So most of them are stacked towards below 0.05. What I would suggest you do if you're doing a histogram is truncate at sort of obscenely large p-values. And what we can do to do that is we just do Keanu, where Keanu is less than 0.2. That gives us, oh no, what have I done? Oh, I've spelled it wrong. That's what I've done wrong. then we get a nicer histogram. And if you like, we can also say breaks equals 50. Speaking of which, what time is it? Oh, wow. God, I've only got 15 minutes left. Okay, that gives us like, this is the distribution of p-values, because we know that every time we run a study, our p-value is not going to be exactly the same. And sometimes we're going to have a false positive, sometimes we'll have false negative, sometimes we'll get above, below p-values. But what this histogram does is it tells us the distribution of p-values under this particular configuration. So when we've got 160 participants and a mean difference of 0.5, we've got most of our p-values are stacked towards 0, not at 0, impossible, but towards 0, which is kind of what this is looking like a healthy histogram. Angela's just asked, why does a histogram of p-values look like this? It's because under an alternative hypothesis, under our own hypothesis, with a sufficient amount of sample size, p-values are more likely to be below 0.05. That's just that's a feature of frequentist statistics. That's why we need particular sample sizes. It's not impossible that they'll be above 0.5, but it becomes very much less less likely to see those. Okay, so what I want to ask the chat now. Oh, I can. Yeah, sorry about that. Yeah, I should have been doing this all along. I'll paste my code into the chat now. Thank you, Jorge. There you are. What I want to ask now, I just want to throw a pitch question out now. If our mean difference is 0, so there's literally no difference, what do we think this histogram would look like? Anyone want to drop a question? Oh, bam! This blew my mind when I first learned about it 2 or 3 years ago. Yeah. Okay. So we're gonna see right. So if people don't know what a uniform distribution or a flat distribution looks like, we're gonna do that now. We're gonna simulate what a set of p-values looks like when we have literally 0 effect. So this is population. These two numbers have exactly the same mean. We're gonna run that, and we're gonna run a histogram. We're gonna do it 1,000 times. And as 3 people have already pointed out, we have something called a uniform distribution. And uniform distribution means that every value is equally likely. We've got some sampling error here. If I knock this up to 1,000,000 or 10,000, then it'll probably be a lot flatter. It'll also take longer, yeah. And so what happens is asymptotically, it ends up with as a flat distribution. What this means is if you observe a p-value of below 0.05, when your null hypothesis is true, then it's as likely to occur, that number is as likely to occur as anything above 0.05. So just bear that in mind. That's why it's so important to plan your study, like using power analysis correctly. It's so important to bear this in mind, because just because you get a p-value of 0.15 doesn't that is as likely to occur as a p-value of 0.005. So when the null hypothesis is true. Obviously, as we move towards, we get larger and larger effect sizes, the density of our observations pushes, I'm looking like a weather person here, pushes towards towards 0. So it becomes less likely, and that's what we mean in frequent statistics. It's unlikely that the p-value this size would occur if the null hypothesis was false, was true. And so maybe just apprise yourself of that. And if you observe a p-value of 0.15 in a data set, it's really unlikely that that's occurred in a when there's actually an effect. So if we just, I'm just gonna we'll go back to 0.5 here, and we'll do another 10,000 simulations. So it's 0.15 is really rare when we have well-powered study and there's an actual effect, but a lot less, but a lot more likely, and as likely as significant p-values when there's no effect. Okay, cool. Thank you. I've whittled on long enough there, I think. Okay, so one thing, should we do nested loops? I've got maybe 5 minutes. Should we do it? Let's do a nested loop. We're going to do a nested loop. This is going a bit advanced, but we're gonna do it. Okay, so what we're going to do now is we're going to try and plot a power curve. Okay, yeah, we are. Shall we? Who wants me to plot a power curve? Yeah, okay, let's plot a power curve. Let's find my notes. Okay, so what we're going to do is we're going to run not just 1,000 repeats, we're going to run 7,000 repeats, and we're going to have 7 different sample sizes. Okay. For this, we do something called a nested loop. So we're going. What we're going to do is we're going to do some. We're going to go a bit inception. We're going to do a loop within a loop. So we need to create. First of all, we need to create another matrix. So we're going to create a matrix. I'm going to call this Morpheus. Morpheus is equal to n row equals 7, and we're going to have 2 columns this time. 2 columns. N col equals 2. So what this is going to do is we're going to have in one side we're going to have sample sizes, and in the other column we're going to have powers as we go along. And this is the thing we're going to be plotting later on. So we've got Morpheus is equal to the matrix, a matrix with 7 rows and 2 columns. Create that. In fact, just for cleanliness again, I'm just going to delete all the objects. We start all over again. So we've got Morpheus here. Okay. We also need a second index. Oh, right. Okay. We also need a set of sample sizes. So we're going to have we're going to use let's call it sizes for now. Sizes is equal to C, which means concatenate. C, I'm going to go 10, 20, 30, 40, 50, 60, 70. That's 7 entries, giving us 7 different sample sizes. We're now going to start up a second loop. Well, it's technically the first loop. So we're going to go for this size in 1 to n row Morpheus. What n row does is it tells us how many rows Morpheus has. We should have, I should say 7. We're just going to double check that though, because I've done this workshop before and stuff started breaking and it was really embarrassing. So I'm trying to avoid that now. So for this size in 1 to 7, this is going to do. We're going to do all this stuff here 7 times. We're not going to do the histogram though, because that is going to chew stuff up. We want length though, so we're going to stick that there. What this would do now is if we run this, we're going to have Keanu is going to be run 7 times. So we're going to end up with 7,000 applications. Okay. Move this down a bit so we've got full screen. Right. So what we also everything else is exactly the same. So we've now got Keanu, this one, yada yada. What we need to do now is store in Morpheus the sample size and the observed power for that particular set of simulations, and we do that just by going Morpheus, and then in square brackets we've got the row we're interested in is this size. Morpheus this size. So this is going to be Morpheus's first row, and in the first column we want the sample size, and we're going to do for that. We're just going to go sizes and then square brackets. There are quick ways to do this, but I'm just trying to show how everything fits together. Sizes this size. So what this is going to do is on the first run, it's going to put into Morpheus's first row of the first column 10, and then on the second one it will put in 20 straight ahead. We're then going to copy and paste that, and in our second row what we want is we want to know, and I think someone had an excellent, whoa, some of the S's. We've had an excellent shortcut for where is it, for doing power. Where are you? Thank you, Natasha. Okay, what we're going to do is Morpheus column 2 is going to be some Keanu less than 0.05. I think that's going to work. I'm confident. I'm confident that this is going to work. And this will basically run the simulations 7,000 times. We'll end up with a matrix called Morpheus, which contains each of the samples, 10 to 70, and the observed power in each of those. And let's run it. Let's see if it works. This always gives me the howling phantods. Oh, it worked. I need to fix norm in lines 22 and 23. 22. Change. Aha! Excellent. Thank you very much. That's the howling phantoms for you. Brilliant. Well done. Sizes, just testing, as my maths teacher used to say. This size. So what we're doing here is we need to change 80 to the index of sizes. So sizes, this size gives us, and now what this will do is iterate properly. Thank you so much. I would have missed that, and I would have made some grand claims about something probably. Yeah, sizes, typo, Morpheus, go. Huzzah! All right, now what we can do is just plot Morpheus. And that's our power curve. We see that at, I mean, we could divide this by 10 to get percentages, but just, you can do that in your head. At 10 participants, we're on 20% power. 20 participants, we're on pushing 40%, all the way up to 70 when we're pushing 80% power, which is good stuff. So yeah, brilliant sample size. Yeah, and that is how you do. And if you want, you could do in lines rather than. Now, no, beautiful is when you use ggplot. And if you do use lines there, then it actually plots it. And then, so we can also play around as well. So maybe we'll just play around quickly. We've got a couple of minutes left. Mean is 0.05. Let's change this to 0.7. You can run it again. And again, you can have a loop within a loop within a loop if you wanted. And you would end up with, you could have like a fancy, but there's a worksheet on that if you're interested. So we're going to go to plots, Morpheus. We end up, our bare minimum is a power of 40 in that case, etc. Our norm isn't restricted to a standard normal distribution. We can also go on to intelligence tests. So we've got a mean of 100, a standard deviation of 15, which is what standard IQ is. And we're going to give someone a drug. We're going to give them, I don't know, Adderall or some sort of drug. And we're going to say that this has an effect of increasing someone's IQ by 115. It doesn't, but we're just saying this is a drug that we've just invented that increases people's intelligence by 1 standard deviation. And we can run that now, and we'll run that, and that's going to say, okay, so how many people we have to give this drug to in order to get that? Not many at all, because we've got such a huge effect size that that plotting it is just. I'm whittering now. Yeah, we start off at 60% power, so that'd be a pretty good drug. I'd probably take it. I think I'd probably need that drug. Okay, I've talked for an hour and a half straight, and I think. Oh, repeated measures fraction time day. Now, Lisa defines. This is under the hood of what Faux does. And Faux does everything and more. So I would really suggest checking out the video on YouTube about using Faux if you want to do mixed designs and things like that, because that will do everything you need to do and everything. If you want to compare the power of 2 independent t-tests, you can write it in the same loop. Yeah, absolutely. Is MV1 our constant linear model base? That would be our control group. Yes, that's our control group. Thank you, Matt. Excellent. So MV1 would be is our like it's a placebo group. These people given sugar pills. The people in MV2 got given well, maybe sugar pills might I don't know, extra glucose. So sugar pills, and the people in the other group were given this special drug that makes you super smart. Okay, I'm glad. Thank you very much, Duncan. Okay, I think we'll leave it there. Oh, brilliant. Thank you so much. Okay, so a video will be available on YouTube if you need it. We've got on, we're doing power analysis for linear regression with Mark Adkins, no, Andrew Hayes. Is it Andrew Hayes? Andrew Hayes on Wednesday, I want to say. So I'll see you all there. Thank you so much for coming along. It's been excellent. Andrew Hales. There. Oh, so sorry. Sorry, Andrew. I'm so sorry. Andrew Hales. Thank you. Take care now. Bye now. That's the OSF for the worksheet. Now, yeah, great. Oh, you want the last bit of code? We'll do that. Okay, right. So Morpheus, pod, and there. Brilliant. Right, this. I'll stop recording. I'm going to stop sharing, and I'll stop recording as well. I'll do that then. Okay.